Imagine a family of worlds drifting through the darkness. 8 planets spinning around a single star. Moons that glow with hidden oceans, rings made of ice and ancient dust, and comets falling silently through the void. That family is your celestial neighborhood, the solar system. Tonight we drift gently from world to world. There is no test at the end. No rush, no urgency. Just the slow unfolding of planetary wonders to carry you peacefully into rest. The sun holds everything together. Its gravity reaches across billions of kilometers, cradling planets in their orbits, guiding comets on their endless journeys, and warming the frozen reaches of distant moons. And yet, for all its power, the sun is just one star among hundreds of billions in our galaxy alone. Tonight we explore our corner of the cosmos, from scorching Mercury to frozen Neptune, from volcanic moons to worlds where diamonds may rain from the sky. All of it waiting to be whispered into the quiet of night. Tonight, let's drift off together while exploring over 100 soothing facts about our solar system. There's no rush here, no test at the end, just soft words and quiet wonders to carry you into rest. Welcome to Drowsy Discovery. I'm glad you found your way here tonight. Perhaps you've had a long day. Or maybe you simply enjoy falling asleep to thoughts of distant worlds and drifting moons. Either way, this journey is for you. There is something deeply calming about contemplating the planets. They have been circling the sun since before life existed on Earth. They have witnessed the rise and fall of species, and they will continue their quiet orbits long after we are gone. So settle in, let your breathing slow, and let the weight of the day drift away like a comet fading into the dark. The solar system is approximately 4.6 billion years old. It formed from a vast cloud of gas and dust that collapsed under its own gravity. At the center of that collapse, the sun ignited. A nuclear furnace that would burn for billions of years. Around it, the remaining material swirled into a flattened disk. Within that disk, particles collided and clumped together. Small rocks became larger rocks. Larger rocks became planetesimals, and planetesimals became planets. This process took millions of years. A slow assembly of worlds from cosmic debris. Tonight, we will visit each of those worlds. We will learn their secrets, and we will drift gently through the space between them. But there is no hurry. The planets have been orbiting for billions of years. They can wait a little longer while you rest. Let us begin with the star at the center of it all. The Sun contains 99.8% of all the mass in the solar system. That number bears repeating. Nearly all of the matter in our entire celestial neighborhood is concentrated in one object: the Sun. Everything else, all 8 planets, all their moons, every asteroid, every comet, every grain of dust, makes up less than 0.25%. The Sun is so massive that it could contain over 1.3 million Earths. If you hollowed it out and poured in our planet, you would need to do so more than 1 million times to fill it. This immense mass is what generates the gravity that holds everything in orbit. Without the Sun, the planets would drift away into the darkness of interstellar space. The Sun loses over 4 million tons of mass every second. Deep within the Sun's core, nuclear fusion is constantly occurring. Hydrogen atoms are squeezed together under immense pressure and temperature, fusing into helium. In this process, a tiny amount of mass is converted into pure energy. This is the energy that lights our days and warms our world. 4 million tons vanishing every second sounds catastrophic. But the Sun is so massive that even at this rate, it has barely changed over the past 4.5 billion years. It will continue burning for another 5 billion years, before exhausting its fuel and beginning its transformation into something else entirely. The Sun's core reaches temperatures of 15 million degrees Celsius. At the very center of the Sun, conditions are almost beyond imagination. The temperature exceeds 15 million degrees. The pressure is 340 billion times the atmospheric pressure at Earth's surface. Under these extreme conditions, hydrogen atoms are stripped of their electrons and forced together so closely that their nuclei fuse. This is the fusion that powers the Sun, the same process that occurs in hydrogen bombs, but sustained continuously for billions of years. The energy generated in the core takes a remarkably long time to reach the surface. Photons bounce and scatter through the dense solar interior, taking hundreds of thousands of years to make the journey outward. Once they escape the surface, they cross the gulf between the Sun and Earth in just over 8 minutes. The light touching your eyelids right now began its journey in the Sun's core before humans existed. The Sun will one day become a red giant and then a white dwarf. Stars do not live forever. They are born, they burn, and eventually they die. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core. Fusion will cease, and the core will begin to collapse under its own gravity. As it collapses, it will heat up. The outer layers of the Sun will expand outward, swelling to enormous size. The Sun will become a red giant, its surface reaching perhaps as far as Earth's current orbit. Mercury and Venus will almost certainly be consumed. Earth's fate remains uncertain, but even if it survives, it will be scorched beyond recognition. After the red giant phase, the Sun will shed its outer layers into space, creating a beautiful shell of glowing gas called a planetary nebula. At the center, the remaining core will cool and fade over trillions of years as a white dwarf, a stellar ember glowing faintly in the darkness. The Sun vibrates like a vast musical instrument. Though we cannot hear it, the Sun is constantly ringing with sound. Pressure waves rise and fall through its blazing layers, creating oscillations that ripple across the entire star. These vibrations are far below the range of human hearing, but scientists can detect them through careful observation. The study of these solar oscillations is called helioseismology. By tracking how the waves travel through the Sun's interior, researchers can map its hidden structure much like geologists use seismic waves to study Earth's interior. The Sun hums with a deep, slow rhythm, a cosmic song that has been playing for billions of years. The Sun's magnetic field flips approximately every 11 years. The Sun is not magnetically stable. Its magnetic field is constantly changing, driven by the motion of electrically charged plasma in its interior. Approximately every 11 years, the magnetic poles of the Sun switch places. North becomes south, and south becomes north. This cycle is tied to sunspot activity, solar flares, and the overall level of solar radiation. At solar maximum, when the field is most chaotic, the Sun produces more flares and coronal mass ejections. At solar minimum, activity quiets down. This 11-year pulse affects everything from satellite operations to the brightness of auroras on Earth. The Sun breathes on an 11-year rhythm, and we feel its breath across millions of kilometers. Mercury is the closest planet to the Sun, yet not the hottest. This seems counterintuitive. Surely the planet nearest to the Sun should be the hottest. But Venus, the second planet, holds that record. The difference lies in atmosphere. Mercury has almost no atmosphere. It has only a thin exosphere, a tenuous shell of atoms blasted from its surface by solar wind. Without an atmosphere to trap heat, Mercury's temperature swings wildly. The sunlit side can reach over 430 degrees Celsius, but the dark side plunges to nearly -180 degrees. Venus, by contrast, has an incredibly thick atmosphere composed mostly of carbon dioxide. This atmosphere traps heat through a runaway greenhouse effect, raising surface temperatures to over 460 degrees Celsius, hot enough to melt lead. Venus is a furnace wrapped in clouds. Mercury is a world of extremes, with no blanket to hold its warmth. Mercury has ice hiding in permanently shadowed craters. Despite being so close to the Sun, Mercury holds frozen water. This ice exists in deep craters near the poles, where the Sun's rays never reach. These permanently shadowed regions act like natural freezers. Temperatures there remain cold enough for water ice to persist for millions of years. Scientists believe the ice may have been delivered by comet impacts or volcanic outgassing long ago. Radar observations from spacecraft have confirmed the presence of bright, reflective deposits in these shadowed regions. On one of the hottest planets in the solar system, ice survives, locked away in darkness. Mercury's core makes up about 80% of its radius. Mercury is an unusual planet. Its iron core is disproportionately large compared to its thin, rocky mantle and crust. No one knows exactly why. One theory suggests that Mercury once had a thicker outer layer that was stripped away by a massive impact early in the solar system's history. Another possibility is that the young sun's intense radiation vaporized lighter materials, leaving behind a metal-rich world. Whatever the cause, Mercury is the densest planet after Earth. Relative to its size, it is essentially a giant iron ball with a thin coating of rock. A year on Mercury is shorter than a day on Mercury would feel. Mercury's orbital period is about 88 Earth days. It circles the Sun faster than any other planet, but its rotation is slow. It takes 59 Earth days to spin once on its axis. Combined with its orbital motion, this creates an unusual situation. A solar day on Mercury, from one sunrise to the next, lasts about 176 Earth days. That is 2 full Mercury years. If you stood on Mercury, you would experience a sunrise, watch the sun slowly cross the sky, and finally see it set, all while the planet completed 2 full orbits around the sun. Time works differently on that scorched little world. Venus rotates backward compared to most planets. Most planets in the solar system spin in the same direction they orbit the Sun. Venus does not. It rotates in the opposite direction, a phenomenon called retrograde rotation. On Venus, the Sun rises in the west and sets in the east. The reason for this backward spin remains uncertain. One possibility is that a massive collision early in Venus's history knocked it over. Another theory suggests that tidal interactions with its thick atmosphere gradually slowed and reversed its rotation over billions of years. Whatever the cause, Venus stands alone as a world spinning against the current. Venus has no moons. Among the rocky planets, Venus is peculiar in having no natural satellites whatsoever. Mercury also lacks moons, likely due to its proximity to the Sun, which makes stable orbits difficult to maintain. Venus, however, is more puzzling. It is roughly the same size as Earth, which has a large moon. Why does Venus have none? Some scientists suggest Venus may once have had a moon that spiraled inward and collided with the planet. Others propose that any moons were stripped away by gravitational interactions with the Sun. Venus orbits alone, a bright wanderer with no companions in its clouded sky. A day on Venus is longer than its year. Venus rotates so slowly that a single day, one complete rotation, takes 243 Earth days. Meanwhile, its orbit around the Sun takes only 225 Earth days. This means that on Venus, a day lasts longer than a year. Combined with its retrograde rotation, this creates one of the strangest day-night cycles in the solar system. The Sun rises in the west, crawls slowly across the sky, and sets in the east, all while the planet completes more than one trip around the Sun. Venus is a world of slow, simmering heat and eerie, extended twilight. Venus's surface pressure would crush you instantly. The atmosphere of Venus is not only hot, but incredibly dense. At the surface, the atmospheric pressure is about 90 times that of Earth's surface. This is equivalent to the pressure you would experience nearly a kilometer beneath the ocean. Any human or unprotected spacecraft would be crushed immediately. The Soviet Venera probes that landed on Venus in the 1970s and 1980s survived for only minutes before succumbing to the heat and pressure. The images they sent back showed a rocky, orange-tinted hellscape beneath oppressive skies. Venus may once have been more Earth-like, with oceans and milder temperatures. But a runaway greenhouse effect transformed it into the hottest world in our solar system. Earth is the only planet known to support life. Among all the worlds we have discovered, Earth remains unique. It is the only place where life is confirmed to exist. Liquid water covers most of its surface. A protective magnetic field shields it from solar radiation. An atmosphere rich in oxygen and nitrogen sustains the breath of countless creatures. Life has existed here for at least 3.5 billion years. It has filled the oceans, colonized the land, and even taken to the skies. Somewhere in the vast cosmos, other life may exist. But for now, Earth stands alone as the only known home of living beings. Tonight, as you rest on this small rocky world, you are part of something rare and precious. Earth has one large moon that stabilizes its axial tilt. The moon is unusually large compared to Earth. No other rocky planet has such a proportionally massive satellite. This relationship is important. The moon's gravitational pull helps stabilize Earth's axial tilt, keeping it within a relatively narrow range over millions of years. Without the moon, Earth's tilt could vary chaotically, potentially swinging from nearly vertical to lying almost on its side. Such dramatic changes would create extreme climate variations that might make complex life difficult to sustain. The moon is more than a companion in the sky. It is a stabilizing influence that may have helped make Earth habitable. The moon is slowly drifting away from Earth. Each year, the moon moves approximately 3.8 centimeters farther from Earth. This gradual retreat is caused by tidal interactions between the two worlds. Earth's tides, raised by the moon's gravity, transfer rotational energy from our planet to the moon, pushing it outward and slowing Earth's rotation in the process. Billions of years ago, the moon was much closer and days on Earth were much shorter. Over time, both have changed. Eventually, the moon will drift so far that it will appear smaller in the sky. Total solar eclipses, where the moon perfectly covers the sun, will no longer be possible. The sky is slowly changing, even if we cannot feel it in a single lifetime. Mars has the tallest volcano in the solar system. Olympus Mons towers nearly 22 kilometers above the surrounding Martian plains. That is almost 3 times the height of Mount Everest. It is so wide that it would cover the entire nation of New Zealand. Its summit caldera alone is over 80 kilometers across. Olympus Mons grew so large partly because Mars lacks plate tectonics. On Earth, volcanic hotspots shift as crustal plates move, creating chains of islands like Hawaii. On Mars, the crust stays still, allowing magma to erupt in the same location repeatedly. Over hundreds of millions of years, layer upon layer of lava built this colossal shield volcano into the tallest mountain on any planet. Mars has the deepest canyon in the solar system. Valles Marineris stretches over 4,000 kilometers across the Martian equator. It is so long that it would span the entire continental United States. In some places, the canyon plunges more than 7 kilometers deep, over 5 times deeper than the Grand Canyon. Scientists believe Valles Marineris formed through a combination of tectonic stretching, volcanic activity, and ancient water erosion. Unlike Earth's canyons, which were primarily carved by rivers, this Martian scar may have opened as the planet's crust cracked and pulled apart. It is a wound in Mars's surface, hinting at a violent geological past now frozen in time. Mars experiences planet-wide dust storms. Mars is known for its rusty, desert landscape, and for the colossal dust storms that sometimes engulf the entire planet. These storms can last for weeks or even months, blocking out sunlight and reshaping the surface. The dust is incredibly fine and can remain suspended in the atmosphere for long periods. Some storms begin as small, localized gusts, but can grow rapidly due to feedback loops between heat, wind, and topography. In 2018, a global dust storm led to the end of NASA's Opportunity rover mission. Its solar panels were choked with dust, cutting off its power supply. Even without rain or oceans, Mars remains an active and restless world. Mars has 2 small, irregularly shaped moons. Phobos and Deimos are tiny compared to Earth's moon. They look more like asteroids than traditional spherical moons, irregular, rocky, and pockmarked with craters. Many scientists believe they were once asteroids in the main belt that were captured by Mars's gravity long ago. Their strange orbits and low densities support this theory. Phobos is slowly spiraling toward Mars. In perhaps 50 million years, it will either crash into the planet or break apart into a ring of debris. Deimos, meanwhile, is gradually drifting away. These 2 small moons are quiet passengers in orbit, remnants of a chaotic past. The asteroid belt contains millions of rocky objects but is mostly empty space. Between Mars and Jupiter lies the asteroid belt, a region populated by millions of rocky bodies. But despite the name, it is not densely packed. If you flew a spacecraft through the asteroid belt, you would almost never encounter an obstacle. The asteroids are separated by vast distances. The entire mass of the asteroid belt is less than 5% of the Moon's mass. Most of that mass is concentrated in a few large objects like Ceres and Vesta. The belt represents material that never formed into a planet. Jupiter's immense gravity stirred the region so violently that the rocky fragments could never coalesce into a larger world. These are ancient building blocks, left over from the solar system's formation. Ceres is both an asteroid and a dwarf planet. Ceres is the largest object in the asteroid belt, so large that it qualifies as a dwarf planet. It was discovered in 1801 and was originally classified as a planet before being reclassified. Ceres is spherical unlike smaller, irregularly shaped asteroids. It may contain a subsurface layer of briny water or mud beneath its icy crust. NASA's Dawn spacecraft revealed mysterious bright spots on its surface, which turned out to be deposits of salt, possibly left behind by evaporating water. Ceres is a hybrid world, offering a glimpse into the early ingredients of planetary formation. Jupiter is so massive, it could contain all other planets combined. Jupiter is the giant of our solar system. It has more mass than all the other planets, moons, asteroids, and comets combined, with room to spare. Over 1,000 Earths could fit inside Jupiter's volume. Its immense size is the result of its position in the early solar system, where it gobbled up vast quantities of hydrogen and helium from the primordial disk. If Jupiter had been about 80 times more massive, it might have ignited nuclear fusion in its core and become a star. Instead, it remains a failed star, a gas giant glowing faintly with its own internal heat. Jupiter radiates more heat than it receives from the Sun. Unlike most planets, Jupiter gives off more energy than it absorbs. This internal glow comes from leftover heat from its formation, a kind of gravitational energy released when the planet's immense mass collapsed together billions of years ago. Even now, Jupiter continues to contract slightly, generating heat in the process. This warmth drives Jupiter's turbulent weather systems, including its massive storms and swirling cloud bands. In the infrared spectrum, Jupiter shines brightly, like a smoldering ember beneath its cloud layers. Jupiter has more than 90 moons. Jupiter is not just the largest planet, it is also the king of moons. As of now, astronomers have identified over 90 natural satellites orbiting Jupiter, and new ones are still being discovered. The four largest, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who first observed them in 1610. Beyond these giants lies a swarm of smaller, irregular moons, many captured from passing asteroids. Some orbit backward, some are only a few kilometers across. Together, they form a miniature solar system in orbit around Jupiter. Io is the most volcanically active body in the solar system. Jupiter's moon Io is a seething, restless world covered in active volcanoes. Its surface is constantly reshaped by eruptions of molten sulfur and rock. Some volcanic plumes rise hundreds of kilometers into space, painting the landscape in vivid yellows, reds, and blacks. This extreme activity is driven by tidal heating. Io is squeezed and stretched by Jupiter's gravity, along with gravitational tugs from neighboring moons. The friction from this constant flexing heats the interior, powering its furious geology. Io is a moon with a molten heart, never at rest. Europa may hide a vast ocean beneath its icy shell. Beneath the frozen surface of Jupiter's moon, Europa lies strong evidence for a subsurface ocean of liquid water. Tidal forces from Jupiter's gravity flex Europa's interior, generating heat that may keep this hidden ocean from freezing solid. The surface is streaked with dark lines and ridges, signs of shifting ice. Spacecraft have detected magnetic signatures and chemical traces consistent with a salty ocean. What makes Europa especially fascinating is the possibility that this hidden sea could harbor life. It is a dark, alien ocean, warmed from below, sealed beneath ice, yet potentially rich with the ingredients for biology. Ganymede is the largest moon in the solar system. Jupiter's moon Ganymede is larger than the planet Mercury. With a diameter of over 5,000 kilometers, it is the biggest natural satellite orbiting any planet. Ganymede has a rocky core, a possible subsurface ocean, and a crust covered in ridged ice and ancient scars. Uniquely, Ganymede is the only moon known to have its own magnetic field, which creates shimmering auroras in its thin atmosphere. Despite its size and complexity, Ganymede remains quiet and dark, orbiting deep within Jupiter's magnetic grasp. Jupiter's Great Red Spot has been raging for centuries. The Great Red Spot is a massive storm swirling in Jupiter's southern hemisphere. It is wide enough to swallow 2 or even 3 Earths. First observed through telescopes in the 17th century, the storm has been raging for at least 350 years, possibly longer. Its reddish color may be caused by complex chemical reactions in Jupiter's atmosphere, triggered by sunlight and high-altitude compounds. Wind speeds along its outer edges exceed 400 kilometers per hour. While Earth's storms last days or weeks, this Jovian tempest has endured for centuries. Jupiter's magnetosphere is the largest structure in the solar system. Jupiter's magnetic field extends millions of kilometers into space, forming a magnetosphere so vast it would appear larger than the Sun if it were visible. This field is powered by electric currents in the planet's metallic hydrogen interior. Within the magnetosphere, charged particles race along magnetic field lines, creating intense radiation belts, massive auroras, and fierce electrical storms. For spacecraft, Jupiter's radiation environment is a major hazard. For scientists, it is a laboratory for studying planetary magnetism at its most extreme. Saturn's rings are made mostly of water ice. Saturn's magnificent rings are composed of countless individual particles, mostly water ice, ranging from tiny grains to house-sized boulders. These icy fragments orbit in an incredibly thin flat disk, maintained by Saturn's gravity and the influence of small shepherd moons. The ice gives the rings their brilliant reflectivity, making them one of the brightest features in the solar system when seen from afar. Up close, the rings reveal gaps, wave patterns, and ringlets shaped by gravitational resonances. They are dynamic, ever-changing structures of sculpted ice. Saturn's rings are paper-thin compared to their width. Saturn's rings stretch more than 280,000 kilometers across, yet they are astonishingly thin. In most places, the rings are less than 100 meters thick. If the rings were the size of a football field, they would be thinner than a sheet of paper. Their flatness is maintained by gravitational dynamics and the self-organization of billions of icy fragments. From a distance, they appear solid, but they are delicate and ethereal. Saturn's rings are slowly disappearing. The beautiful rings that encircle Saturn are not permanent. They are gradually falling into the planet, drawn inward by gravity and Saturn's magnetic field. This process, known as ring rain, involves streams of ice particles and charged material drifting inward over time. Observations suggest that the rings may be less than 100 million years old, young by planetary standards, and could vanish entirely within another few hundred million years. Though they seem timeless, Saturn's rings are a temporary spectacle, a shimmering phase in the planet's long existence. Saturn's North Pole features a massive hexagonal storm. At Saturn's North Pole, a cloud pattern spins in the shape of a nearly perfect hexagon. This six-sided jet stream spans over 30,000 kilometers across, wider than Earth. Scientists believe the hexagon forms from the way Saturn's atmosphere rotates and interacts with stable waves of air trapped around the pole. Similar shapes emerge in laboratory experiments when fluids rotate at different speeds. The fact that such geometric order can appear naturally in a planetary atmosphere is both strange and beautiful. Saturn is less dense than water. If you could find a bathtub large enough, Saturn would float. Not because it is hollow, but because its average density is less than that of water. Saturn is composed mostly of hydrogen and helium, giving it a lightness despite its massive size. Its volume is over 700 times that of Earth, but its mass is only about 95 times greater. This low density creates a fluffy, diffuse structure. Saturn's rapid rotation flattens it at the poles and bulges it at the equator. It is a giant made of gas, softly puffed into shape by gravity and motion. Titan is the only moon with a thick atmosphere. Saturn's largest moon, Titan, is unique in the solar system. It is the only moon with a dense planet-like atmosphere. This atmosphere is composed primarily of nitrogen, similar to Earth's, but much thicker. The surface pressure on Titan is about 1.5 times that of Earth. Beneath the orange haze lie lakes and rivers, not of water, but of liquid methane and ethane. Titan has weather, including methane rain and seasonal storms. It is a world with familiar shapes, clouds, rivers, and coasts, built from alien chemistry. Titan has lakes of liquid methane. Titan is the only other place in the solar system known to have stable bodies of liquid on its surface. But these lakes are not filled with water. Instead, they consist of liquid methane and ethane, chemicals that would be gases on Earth but remain liquid in Titan's frigid temperatures. Some of these lakes are vast, stretching hundreds of kilometers across frozen landscapes sculpted by hydrocarbon chemistry. Beneath the icy surface, scientists believe a subsurface ocean of water may also exist. Titan is a layered world, with alien seas above and hidden water below. Enceladus sprays water into space. Saturn's tiny moon Enceladus may be small, but it hides a spectacular secret. From its south pole, towering geysers of water vapor and ice crystals erupt into space through cracks known as tiger stripes. These plumes are powered by tidal heating beneath the surface, where friction caused by Saturn's gravitational pull keeps a subsurface ocean in a liquid state. The material in the plumes contains organic compounds, salts, and even signs of hydrothermal activity. Some of the water escapes into space and helps replenish Saturn's E-ring. Enceladus may be one of the most promising places to search for life beyond Earth. Uranus rotates on its side. Most planets spin like tops, tilted slightly on their axes. Uranus is different. It is tipped so far over that it essentially rolls along its orbital path. With an axial tilt of 98 degrees, Uranus's poles point almost directly at the Sun during parts of its orbit. This creates extreme seasons. Each pole experiences 42 years of continuous daylight, followed by 42 years of darkness. The cause of this dramatic tilt is still debated. A massive collision early in the solar system's history may have knocked Uranus on its side. Uranus has faint, dark rings. Though Saturn's rings are the most famous, Uranus also has a ring system, 13 known rings in fact. These rings are much darker and fainter than Saturn's, made of small particles of rock and ice. They were not discovered until 1977, when they blocked the light of a background star during an observation. Because Uranus lies on its side, the rings appear vertical when viewed from above the Sun's north pole. They are subtle, shadowy bands circling a sideways planet. Diamonds may rain inside Uranus and Neptune. Deep within the atmospheres of Uranus and Neptune, conditions may be extreme enough to create something extraordinary, falling diamonds. These ice giants have thick layers of methane gas. Under immense pressure and heat, scientists believe the methane can break apart, releasing carbon atoms that compress into crystalline structures. Laboratory experiments have simulated this process, showing how hydrocarbons can condense into diamond under the right conditions. If this theory is correct, storms of glittering crystals may drift through the deep blue darkness of these distant worlds. Neptune hosts the fastest winds in the solar system. Despite being the farthest known planet from the Sun, Neptune has the most violent winds of any planet. These winds whip through its upper atmosphere at speeds exceeding 2,000 kilometers per hour, faster than the speed of sound on Earth. That is roughly 5 times the speed of a commercial jet. The winds likely derive their energy from the planet's internal heat, which continues to radiate outward despite the freezing conditions at its distance. Neptune's atmosphere is composed mostly of hydrogen, helium, and methane, and the winds carve massive storm systems into its pale blue clouds. Neptune radiates more heat than it receives from the Sun. Like Jupiter, Neptune produces more energy than it absorbs from distant sunlight. It radiates about 2.6 times more energy than it receives. This internal heat drives Neptune's powerful storms and supersonic winds. The exact source remains uncertain, but possibilities include residual energy from formation, slow gravitational contraction, or radioactive decay within its core. Despite its extreme distance from the Sun, Neptune is not a frozen, inert world. It is a planet with a cold exterior, but a warm, restless interior. Neptune was discovered through mathematics. Unlike other planets, Neptune was not discovered by simply looking through a telescope. Astronomers noticed irregularities in Uranus's orbit, tiny deviations that could not be explained by known gravitational influences. In the 1840s, 2 mathematicians working independently used these strange motions to predict the location of a hidden planet. When astronomers pointed their telescopes toward the calculated position, Neptune was there. It was a triumph of celestial mechanics. Neptune was the first planet found on paper before it was seen through glass, a world brought to light by numbers alone. Triton orbits Neptune backward. Neptune's largest moon, Triton, is unique among large moons because it orbits its planet in the opposite direction of Neptune's rotation. This backward path, called retrograde orbit, suggests Triton did not form around Neptune, but was captured from the Kuiper Belt long ago. That capture may have caused dramatic upheaval, potentially disrupting Neptune's original satellite system. Triton is also geologically active, with cryovolcanoes that spew icy material into space. Cold, distant, and moving in reverse, Triton defies expectations at every turn. Triton has geysers of nitrogen. Despite its frigid temperatures, Triton is not entirely dormant. Spacecraft have observed geysers on its surface, plumes of nitrogen gas shooting several kilometers into the thin atmosphere. These geysers may be powered by sunlight warming dark surface materials, causing nitrogen ice to sublimate explosively. Triton's surface is relatively young, suggesting geological activity continues to reshape it. Its strange cantaloupe-like texture may be evidence of internal processes that remain poorly understood. Pluto's orbit is highly elliptical. Pluto does not follow a circular path around the Sun. Its orbit is significantly elliptical and tilted relative to the main plane of the solar system. At its closest approach, Pluto comes within about 4.4 billion kilometers of the Sun. At its farthest, it travels out to about 7.4 billion kilometers. This elliptical orbit means Pluto sometimes travels closer to the Sun than Neptune. This last occurred between 1979 and 1999. Despite this, the two worlds never collide. Their orbits are in a stable resonance. For every 3 orbits Neptune completes, Pluto completes exactly 2. Pluto has a heart-shaped nitrogen glacier. The bright, heart-shaped region on Pluto, called Sputnik Planitia, is a vast plain of nitrogen ice, larger than the state of Texas. This icy heart may sit above a subsurface ocean, kept liquid by heat from radioactive decay beneath the crust. The weight of the ice-filled basin creates gravitational anomalies that hint at denser material below. Pluto's heart is not just a scenic landmark, it may be the surface expression of a hidden world. Pluto's atmosphere expands and contracts. Though Pluto is small and distant, it has a thin atmosphere composed mostly of nitrogen, with traces of methane and carbon monoxide. When Pluto approaches the Sun, surface ices sublimate into gas, causing the atmosphere to expand. As Pluto moves farther away, the atmosphere cools and collapses, freezing back onto the surface. During the New Horizons flyby in 2015, Pluto's atmosphere was visible as a layered blue haze. A fleeting breath of warmth around a world that spends most of its time in deep cosmic winter. The Kuiper Belt is home to thousands of icy objects. Beyond Neptune lies a wide region of icy bodies known as the Kuiper Belt. It stretches billions of kilometers from the Sun and contains countless frozen remnants from the solar system's formation. Pluto is the most famous resident, but other dwarf planets like Eris, Makemake, and Haumea also orbit within this frozen zone. These objects are not stars or planets, but ancient relics, preserved in the cold since the earliest days of the solar system. The Kuiper Belt is a fossil archive, holding clues to how our planetary neighborhood came to be. Eris is slightly smaller than Pluto but more massive. When Eris was discovered in 2005, it was initially thought to be larger than Pluto. Its discovery helped trigger the reclassification of Pluto as a dwarf planet. Later measurements revealed Eris is slightly smaller in diameter but more massive, suggesting a denser composition. Eris has one known moon, Dysnomia, and orbits far beyond Pluto, in a highly elliptical path that takes it from the Kuiper Belt nearly into the inner reaches of the scattered disk. It is one of the most distant objects we have observed in our solar system. Comets are ancient remnants of the solar system's birth. Comets are icy bodies that travel on elongated orbits, sometimes taking thousands or even millions of years to complete a single journey around the Sun. They are composed of ice, dust, and rocky material, often described as dirty snowballs or icy dirt balls. When a comet approaches the Sun, its ices begin to sublimate, releasing gas and dust that form a glowing coma and sometimes spectacular tails. Comets are messengers from the distant past, carrying material that has remained largely unchanged since the solar system formed. Comet tails always point away from the Sun. As a comet nears the Sun, solar radiation and the solar wind push material away from the nucleus, forming tails that can stretch millions of kilometers. But these tails do not trail behind like smoke from a train. They always point away from the Sun, regardless of the comet's direction of travel. A comet approaching the Sun has its tail streaming behind it. A comet departing the Sun travels tail first, with the tails leading the way. Solar wind and radiation pressure sculpt these luminous streamers, painting the darkness with ice and light. The Oort cloud may extend nearly a light-year from the Sun. Far beyond the Kuiper belt lies a hypothetical shell of icy objects called the Oort cloud. It has never been directly observed, but its existence is inferred from the orbits of long-period comets. The Oort cloud may contain trillions of icy bodies, loosely bound to the Sun at distances up to 50,000 astronomical units, nearly a light-year away. This marks the true edge of the Sun's gravitational influence. Beyond the Oort cloud lies interstellar space, where the gravity of other stars begins to dominate. Some asteroids have their own moons. While we often picture asteroids as solitary wanderers, many of them have moons. Smaller bodies orbit around them, captured or co-formed companions. The first asteroid moon discovered was Dactyl, orbiting the asteroid Ida. It was revealed by the Galileo spacecraft in 1993. Since then, dozens more asteroid moon systems have been found, including some with multiple moons or strange binary arrangements where two asteroids orbit each other. Even in the vastness of space, gravity links the smallest of objects into quiet partnerships. Vesta has a layered structure like a planet. Vesta is the second largest object in the asteroid belt, but it is not just a rock. It has differentiated layers, including a metallic core, a rocky mantle, and a crust. This means Vesta once had enough internal heat to melt and separate into distinct layers, a process called planetary differentiation. The giant Rhea Silvia crater at its south pole may have exposed some of these deeper layers. Vesta is a frozen protoplanet, a planetary building block that never grew into a full world. The solar system is still being explored by spacecraft. At this very moment, robotic explorers built by human hands are journeying through the solar system. Voyager 1 and 2 have crossed into interstellar space, still transmitting faint signals from beyond the heliosphere. New Horizons has visited Pluto and continues deeper into the Kuiper belt. Juno orbits Jupiter, studying its storms and magnetic field. Perseverance explores Mars, searching for signs of ancient life. We are not merely observers of the solar system. We are participants in its story. The Voyager probes carry golden records. Launched in 1977, Voyager 1 and Voyager 2 each carry a golden record, a phonograph disc containing sounds and images chosen to represent life on Earth. The records include greetings in dozens of languages, music from around the world, and recordings of nature, from bird song to ocean waves to human laughter. Designed by a team led by Carl Sagan, these records are messages in a bottle, cast into the cosmic ocean. If any intelligent beings ever find them, they will hear the voices of Earth, whispering across the gulf between stars. The Parker Solar Probe is touching the Sun. Launched in 2018, NASA's Parker Solar Probe is the first spacecraft to fly directly into the Sun's outer atmosphere, the corona. It travels at extraordinary speeds, faster than any object ever built, and endures temperatures exceeding 1,000 degrees Celsius. Protected by a carbon composite heat shield, the probe dips closer to the Sun with each orbit, gathering data on solar wind, magnetic fields, and energetic particles. It is not just studying the Sun, it is flying through it. The heliosphere is a magnetic bubble protecting the solar system. The solar wind, a stream of charged particles from the Sun, flows outward in all directions, forming a vast magnetic bubble called the heliosphere. This bubble shields the solar system from much of the galactic cosmic radiation that permeates interstellar space. At the outer edge, where the solar wind meets the interstellar medium, lies the heliopause. Beyond it is true interstellar space. As the Sun orbits the Milky Way, the heliosphere moves with it, protecting our planetary family as we drift through the galaxy. Sunlight takes over 8 minutes to reach Earth. Light travels at nearly 300,000 kilometers per second, the fastest speed in the universe. Yet even at this velocity, sunlight needs about 8 minutes and 20 seconds to cross the gulf between the Sun and Earth. This means that when you see the Sun, you are not seeing it as it is now, but as it was 8 minutes ago. If the Sun were to suddenly vanish, we would not know for over 8 minutes. We live in the light of the recent past. Light from the Sun takes over 4 hours to reach Neptune. As distances increase, so does the time light needs to travel. Light reaching Earth takes about 8 minutes. Light reaching Jupiter takes about 43 minutes. Light reaching Neptune takes over 4 hours. A message sent from Earth to a spacecraft at Neptune would take that long to arrive, and another 4 hours for the reply to return. The solar system is vast. Even light, the fastest thing in existence, needs hours to cross it. The solar system completes one galactic orbit every 225 million years. While the planets orbit the Sun itself is moving. It revolves around the center of the Milky Way galaxy. This galactic orbit takes approximately 225 million years to complete, a journey sometimes called a galactic year. The last time Earth was in this position relative to the galactic center, dinosaurs were beginning to dominate the planet. We are not fixed in space. We are part of a vast, slow spiral, riding through the galaxy on a journey billions of years long. Planetary atmospheres slowly leak into space. Even thick atmospheres like Earth's are not permanent. Over time, light gases like hydrogen and helium can escape a planet's gravity and drift into space. This process, called atmospheric escape, is more pronounced on smaller worlds with weaker gravity. Mars has lost most of its original atmosphere. Venus, lacking a magnetic field, has seen its upper atmosphere eroded by the solar wind. Earth loses thousands of tons of hydrogen each year, though it is easily replenished. It is a slow, silent exchange between planets and the void. The Moon has quakes. Though it appears still and silent, the Moon occasionally trembles. These moonquakes can be caused by tidal forces from Earth's gravity, thermal expansion as the lunar surface heats and cools, or meteorite impacts. Some quakes originate deep within the Moon and can last for up to an hour, far longer than typical earthquakes. The Moon has no tectonic plates, but its quakes suggest an interior that is not entirely dormant. A solid world with a quiet, pulsing heart. Earth's magnetic field shields us from solar radiation. Surrounding our planet is an invisible magnetic field generated by the movement of molten iron in Earth's outer core. This magnetic field deflects charged particles from the Sun, protecting the atmosphere and surface from harmful radiation. Without it, the solar wind would gradually strip away our atmosphere. The field also funnels some particles toward the poles, where they create the shimmering curtains of aurora. Earth's magnetosphere is a dynamic shield, essential for preserving both life and climate. The Sun's corona is hotter than its surface. This is one of the strangest facts about our star. The visible surface, or photosphere, has a temperature of about 5,500 degrees Celsius. But the outer atmosphere, the corona, can reach over 1 million degrees. How the corona becomes so much hotter than the surface below remains an open question. Theories involve magnetic waves transferring energy outward or tiny explosions, called nanoflares, releasing heat. The Sun's outer layers glow with mysterious searing energy far beyond their source. Solar flares can disrupt technology on Earth. Solar flares are sudden, powerful eruptions of energy from the Sun's surface. They release intense bursts of radiation across the electromagnetic spectrum. When directed toward Earth, they can disturb the upper atmosphere, affecting GPS systems, radio communications, and satellite operations. In extreme cases, they can trigger geomagnetic storms that threaten power grids. The Sun is not a steady light. It is a dynamic, volatile star that occasionally sends ripples of energy across the solar system. Auroras are caused by solar particles interacting with Earth's atmosphere. The shimmering curtains of green, red, and violet light near Earth's poles are auroras. They occur when charged particles from the Sun, channeled by Earth's magnetic field, collide with atmospheric gases. These collisions excite atoms of oxygen and nitrogen, causing them to glow. Auroras become more frequent and intense during periods of high solar activity. During solar maximum, increased sunspot activity sends more particles toward Earth, fueling brighter displays. The Sun's breath paints our polar skies in light. There may be undiscovered planets beyond Neptune. Astronomers have noticed that some distant objects in the Kuiper Belt follow clustered, elongated orbits that cannot be easily explained by the known planets. One theory suggests that a large, undiscovered planet, sometimes called Planet 9, may be gravitationally influencing these distant paths. If it exists, This hidden planet would be several times the mass of Earth and orbit far beyond Pluto, taking thousands of years to complete a single revolution. The search continues. If found, it would reshape our understanding of the solar system's outer architecture. The solar system may have lost planets early in its history. Computer simulations suggest the early solar system was more chaotic than it is today. Planetary orbits were less stable, and gravitational interactions may have ejected some worlds entirely. It is possible that planets once orbited where now only debris remains. Some may have been flung into the darkness of interstellar space, becoming rogue planets wandering between the stars. The solar system we see today is the survivor of a turbulent youth. Only the worlds that found stable orbits remained. The planets formed in a specific order based on temperature. Close to the young sun, where temperatures were high, only rock and metal could condense from the primordial disk. This is why Mercury, Venus, Earth, and Mars are rocky worlds with solid surfaces. Farther out, beyond a boundary called the frost line, temperatures were cold enough for water and other volatiles to freeze. Ice could accumulate alongside rock, allowing the outer planets to grow much larger. Jupiter and Saturn formed in this cooler region, gathering vast envelopes of hydrogen and helium around their cores. Uranus and Neptune formed even farther out, in a zone where growth was slower, but ices were abundant. The architecture of the solar system is a frozen record of temperature gradients in the ancient solar nebula. Mercury has no seasons. Unlike Earth, which has seasons because of its tilted axis, Mercury has almost no axial tilt. Its spin axis is nearly perpendicular to its orbital plane. This means there is no variation in the angle of sunlight throughout Mercury's year. The poles never experience the extended daylight or darkness that Earth's poles do. However, Mercury does have craters at its poles that are permanently shadowed, where ice can survive despite the planet's proximity to the Sun. Without seasons, Mercury is a world of extremes defined purely by day and night, not by the slow turning of hemispheres toward and away from the Sun. Venus is often called Earth's twin. In terms of size, mass, and composition, Venus is remarkably similar to Earth. The two planets are nearly the same diameter and have similar densities. Some scientists believe Venus may have once had oceans and a more temperate climate. But a runaway greenhouse effect transformed it into a hellish world. Despite their similarities, Venus and Earth evolved along dramatically different paths. One became a cradle for life. The other became a furnace wrapped in acid clouds. Understanding what happened to Venus may help us understand the future of our own planet. Venus has been visited by more spacecraft than any other planet. The Soviet Venera program sent multiple probes to Venus in the 1960s through 1980s. Several of them successfully landed on the surface and transmitted images before succumbing to the extreme conditions. American missions like Mariner and Pioneer also explored Venus from orbit. More recently, the European Venus Express studied the planet's atmosphere for years. Despite this attention, much about Venus remains mysterious. Its thick cloud cover hides the surface from view, and the extreme conditions make long-term exploration difficult. New missions are being planned to return to Venus and explore its geology, atmosphere, and possible volcanic activity. Earth's atmosphere is mostly nitrogen. Although we often think of oxygen as the defining gas of our atmosphere, nitrogen actually makes up about 78% of the air we breathe. Oxygen accounts for about 21%, with the remaining 1% consisting of argon, carbon dioxide, water vapor, and trace gases. This nitrogen-oxygen balance is maintained by biological and geological processes. Plants produce oxygen through photosynthesis. Volcanic eruptions release gases from the interior, and the ocean exchanges gases with the atmosphere. The air you breathe is the product of billions of years of planetary chemistry. Earth's oceans contain 97% of the planet's water. Most of Earth's water is salty. The oceans, seas, and saltwater bodies contain the vast majority of the planet's liquid water. Fresh water makes up only about 3%, and most of that is locked in ice caps and glaciers. Less than 1% is available in rivers, lakes, and underground aquifers. This small fraction of accessible fresh water sustains nearly all terrestrial life. It is constantly recycled through the atmosphere, falling as rain and returning to the sea. Water is Earth's defining feature, but the water we rely on daily is surprisingly rare. Mars once had flowing water on its surface. Evidence from rovers, orbiters, and landers suggests that Mars was once a wetter world. Ancient river valleys, dried lake beds, and mineral deposits all point to a time when liquid water flowed across the surface. Billions of years ago, Mars may have had lakes, rivers, and perhaps even a shallow ocean in its northern hemisphere. What happened to all that water remains a mystery. Some of it likely escaped to space as Mars lost its atmosphere. Some may be locked in subsurface ice or bound within minerals. The ghost of ancient water haunts the Martian landscape. Mars has seasons similar to Earth's. Because Mars has an axial tilt similar to Earth's, about 25 degrees compared to our 23, it experiences seasons. During Martian winter, polar ice caps expand. During summer, they shrink. Dust storms often intensify during seasonal transitions. However, Martian seasons last nearly twice as long as Earth's, because Mars takes almost 2 Earth years to complete one orbit around the Sun. The red planet follows a familiar rhythm of change, stretched across a longer year. The asteroid belt was shaped by Jupiter's gravity. Jupiter's immense mass prevented the material in the asteroid belt from ever forming into a planet. Its gravitational influence stirred the region so violently that collisions were more destructive than constructive. Instead of building up into a larger body, the asteroids were ground down, scattered, and prevented from coalescing. Jupiter continues to influence the belt today, creating resonances that clear gaps and cluster asteroids into specific orbital families. The giant planet is both guardian and sculptor of the asteroid belt, shaping it from afar. Some asteroids are made of metal. Not all asteroids are rocky. Some are composed primarily of iron and nickel, remnants of the cores of ancient protoplanets that were shattered by collisions. These metallic asteroids are extremely dense and reflective. Scientists believe they represent the exposed interiors of differentiated bodies, worlds that once had molten cores before being broken apart. Asteroid mining proposals often focus on these metallic bodies because of their potential mineral wealth. They are fragments of worlds that almost were, their iron hearts laid bare by violence long ago. Jupiter's clouds contain bands of different colors. When we look at Jupiter, we see alternating light and dark bands stretching across its atmosphere. These bands are cloud layers at different altitudes, moving at different speeds. The light zones are regions of rising gas and higher clouds. The dark belts are areas of sinking gas and deeper clouds, revealing different chemical compositions. Ammonia ice, ammonium hydrosulfide and water are among the compounds that give Jupiter its varied palette. The planet's rapid rotation, just under 10 hours per day, stretches these features into the familiar striped pattern. Jupiter's moon Callisto is heavily cratered. Unlike the other Galilean moons, Callisto shows no signs of recent geological activity. Its surface is ancient and heavily scarred by billions of years of impacts. Callisto is one of the most heavily cratered objects in the solar system. Its surface is a record of bombardment stretching back to the earliest days of the solar system. Despite its apparently dead surface, magnetic measurements suggest Callisto may have a subsurface ocean hidden beneath its icy crust. A frozen world with a secret heart. Saturn takes 29 Earth years to orbit the Sun. Saturn moves slowly through the zodiac, taking nearly 3 decades to complete one journey around the Sun. This leisurely pace means that Saturn's seasons are long. A single Saturnian season lasts over 7 Earth years. Ancient astronomers noticed Saturn's slow motion and associated it with age and time. In many cultures, Saturn was connected to concepts of patience and endurance. Watching Saturn move through the constellations is watching time unfold on a planetary scale. Saturn's moon Mimas looks like the Death Star. Mimas is a small, icy moon dominated by a giant impact crater called Herschel. The crater is so large relative to the moon that it gives Mimas a striking resemblance to the Death Star from Star Wars. The impact that created Herschel nearly shattered Mimas entirely. A slightly larger collision would have destroyed the moon. Despite its small size, Mimas has a significant gravitational influence, helping to shape the gaps in Saturn's rings. Saturn's moon Hyperion has a sponge-like appearance. Hyperion is one of the strangest moons in the solar system. Its surface is covered with deep, sharply defined craters, giving it a sponge-like or honeycomb texture. The moon is irregularly shaped and tumbles chaotically through space, rather than spinning in a predictable way. Its low density suggests it may be a rubble pile, a loosely bound collection of ice and rock rather than a solid body. Hyperion is a cosmic oddity, a tumbling sponge in orbit around the ringed giant. Saturn's moon Iapetus has 2 faces. Iapetus is a moon of dramatic contrasts. One hemisphere is as dark as charcoal, while the other is bright as snow. Scientists believe this two-toned appearance is caused by dust from other moons falling onto Iapetus's leading hemisphere, darkening it over time. The dark material absorbs more sunlight, warming and evaporating water ice, which then migrates to the brighter trailing hemisphere. This feedback process has created one of the most visually striking moons in the solar system. A world divided by light and shadow. Uranus was the first planet discovered with a telescope. The planets visible to the naked eye have been known since ancient times. But Uranus was too faint to be seen without optical aid. In 1781, astronomer William Herschel observed Uranus through his telescope and initially thought it was a comet or star. Further observations revealed its planetary motion. The discovery of Uranus expanded the known boundaries of the solar system and ushered in an era of instrument-based astronomy. A planet that had waited in darkness for millennia was finally seen. Uranus has 27 known moons. The moons of Uranus are named after characters from the works of William Shakespeare and Alexander Pope. The 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, are substantial worlds with varied surfaces. Smaller moons orbit closer to the planet or follow more distant, irregular paths. Miranda in particular is famous for its dramatic, fractured surface, including a cliff called Verona Rupes that may be the tallest known cliff in the solar system. A family of moons named for literature, orbiting a world turned on its side. Neptune appears blue due to methane in its atmosphere. The vivid blue color of Neptune is caused by methane gas in its upper atmosphere. Methane absorbs red light from the sun and reflects blue light back into space. This gives Neptune its distinctive azure appearance, similar to, but more intense than Uranus. Beneath the blue clouds, Neptune's atmosphere transitions into denser layers, where conditions become increasingly extreme. The planet's color is a window into its atmospheric chemistry. Neptune has a large dark spot that comes and goes. When Voyager 2 flew past Neptune in 1989, it observed a massive storm system called the Great Dark Spot. Similar in some ways to Jupiter's Great Red Spot, this storm was an anticyclonic vortex larger than Earth. However, when the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had vanished. Other dark spots have appeared and disappeared since then. Unlike Jupiter's long-lived storms, Neptune's appear to be more transient, forming and dissipating over years or decades. The planet's atmosphere is dynamic and ever-changing. Neptune has only been visited by one spacecraft. Voyager 2 remains the only spacecraft to have flown past Neptune. In August 1989, it passed within 5,000 kilometers of the planet's cloud tops. During this brief encounter, Voyager 2 captured images, measured atmospheric composition, and discovered new moons and ring arcs. No other mission has returned to Neptune since. Future proposed missions could take decades to reach this distant world. Our knowledge of Neptune comes largely from a single fleeting visit. Pluto has 5 known moons. The most famous is Charon, which is so large relative to Pluto that the two are sometimes considered a binary system. They orbit a common point in space that lies between them, rather than Charon orbiting Pluto directly. The 4 smaller moons, Nix, Hydra, Kerberos, and Styx, are tiny by comparison and may have formed from debris generated during the same collision that created Charon. Pluto and its moons form a compact, complex system at the edge of the solar system. Pluto was reclassified as a dwarf planet in 2006. For decades, Pluto was considered the 9th planet. But as more Kuiper Belt objects were discovered, some comparable in size to Pluto, astronomers reconsidered its classification. In 2006, the International Astronomical Union defined a new category called dwarf planet. Pluto met most criteria for planethood, but had not cleared its orbital neighborhood of other debris. The reclassification was controversial, but reflected a growing understanding of the solar system's outer reaches. Pluto remains a fascinating world, regardless of its classification. Haumea is one of the fastest rotating objects in the solar system. This dwarf planet in the Kuiper Belt completes a rotation in just under 4 hours. This rapid spin has stretched Haumea into an elongated football-like shape. Haumea also has a ring and 2 small moons, Hiaka and Namaka. Its surface is covered in crystalline water ice. The fast rotation may have been caused by a collision that also created Haumea's moons and ring. A rapidly spinning, football-shaped world tumbling through the outer darkness. Makemake has no known moons, except possibly one. For years, Makemake appeared to be a solitary dwarf planet. But in 2016, a small moon was discovered orbiting it, temporarily designated S2015. This moon is very faint and difficult to observe, which is why it took so long to find. Makemake itself is one of the brightest objects in the Kuiper Belt, covered in methane ice that reflects sunlight. Even the smallest worlds can have companions. Some meteorites on Earth came from Mars. Pieces of Mars have been found on Earth. These Martian meteorites were blasted off the red planet's surface by powerful impacts and eventually fell through our atmosphere. Scientists identify them by comparing their chemical composition to data collected by Mars rovers and orbiters. Some of these meteorites contain tiny bubbles of trapped Martian atmosphere. Others show mineral signatures consistent with past water. They are samples from another world, delivered to us by nature. Some meteorites on Earth came from the Moon. Similarly, lunar meteorites have been found on Earth. These are fragments of the Moon ejected by asteroid impacts. Comparing these meteorites to samples returned by the Apollo missions has confirmed their lunar origin. Finding pieces of the Moon on Earth reminds us that the solar system is not a collection of isolated worlds. Material travels between bodies, creating connections across millions of kilometers. The Kuiper Belt was predicted before it was observed. In the mid-20th century, astronomers proposed that a belt of icy bodies might exist beyond Neptune, left over from the solar system's formation. It was not until 1992 that the first confirmed Kuiper Belt object, other than Pluto, was discovered. Since then, hundreds of Kuiper Belt objects have been found. The prediction of the Kuiper Belt was a triumph of theoretical astronomy, anticipating a hidden population based on models of planetary formation. Short-period comets come from the Kuiper Belt. Comets that return to the inner solar system within about 200 years typically originate in the Kuiper Belt. Their orbits have been gravitationally nudged inward by the giant planets. Halley's Comet, which returns approximately every 76 years, is a famous example of a short-period comet. These icy visitors carry ancient material from the outer solar system, preserved since the earliest days of planetary formation. Long-period comets may come from the Oort cloud. Comets with orbital periods of thousands or millions of years are thought to originate in the distant Oort cloud. These comets travel on highly elongated paths that take them far beyond the planets before they fall back toward the Sun. A passing star or gravitational tide from the galaxy can disturb the Oort cloud, sending comets on new trajectories into the inner solar system. They are messengers from the edge of the Sun's influence. The solar system is tilted relative to the Milky Way. The plane of the planets, called the ecliptic, is not aligned with the plane of the Milky Way galaxy. Instead, it is tilted at about 60 degrees. This means that when we look at the Milky Way in the night sky, it does not trace the same path as the planets. The reason for this tilt lies in the random orientation of the gas cloud that collapsed to form the Sun. The solar system inherited an arbitrary spin from its birth. The Sun is about halfway through its life. At approximately 4.6 billion years old, the Sun has consumed about half of the hydrogen fuel in its core. It has another 5 billion years of stable burning ahead before it begins the transformations that will turn it into a red giant and then a white dwarf. We live in the middle chapter of our star's biography. The beginning is ancient history. The end is inconceivably far in the future. For now, the Sun shines steadily, a constant in a changing cosmos. Planetary rings may form from shattered moons. When a moon ventures too close to a planet, tidal forces can tear it apart. The debris spreads into a ring around the planet. This boundary, called the Roche limit, defines how close a moon can orbit before being destroyed by tidal stresses. Saturn's rings may have formed from the destruction of a moon, or moons in the distant past. Similar processes may explain rings around Jupiter, Uranus, and Neptune. Rings are not only remnants of the early solar system. They can also be the remains of destroyed worlds. The Sun has a tail like a comet. As the Sun moves through interstellar space, the solar wind piles up on one side and trails off on the other. This creates a structure called the heliotail. The heliotail is essentially a comet-like tail of charged particles streaming behind the Sun as it orbits the galaxy. It was only recently mapped by the Interstellar Boundary Explorer spacecraft. Understanding the heliotail helps scientists study how the Sun interacts with its galactic environment. Earth's orbit is slightly elliptical. Earth does not travel in a perfect circle around the Sun. Its orbit is an ellipse, though a nearly circular one. At perihelion, Earth's closest approach to the Sun, we are about 147 million kilometers away. At aphelion, the farthest point, we are about 152 million kilometers away. This difference is small, but measurable. It affects the intensity of sunlight we receive, though the effect on seasons is minor compared to axial tilt. The ecliptic is the plane of the solar system. All the major planets orbit the Sun in roughly the same plane, called the ecliptic. This plane corresponds to the original disk of gas and dust from which the solar system formed. The zodiac constellations lie along the ecliptic because they mark the background stars through which the Sun and planets appear to move. The ecliptic is the reference frame for navigating the solar system, the geometric foundation of planetary motion. The outer planets are sometimes called Jovian planets. Jupiter, Saturn, Uranus, and Neptune are often grouped together as the Jovian or giant planets. They are much larger than the inner rocky planets and have thick atmospheres of hydrogen and helium. Jupiter and Saturn are gas giants, composed almost entirely of gas with no solid surface. Uranus and Neptune are ice giants, containing significant amounts of water, ammonia, and methane. These categories reflect not just size, but composition, dividing the planets into fundamentally different types of world. The inner planets are sometimes called terrestrial planets. Mercury, Venus, Earth, and Mars are the terrestrial planets. They are small, rocky, and have solid surfaces. They formed in the warmer inner regions of the solar nebula, where only rock and metal could condense. These worlds are characterized by their density, thin or absent atmospheres, and geological features like mountains, valleys, and craters. They are the planets most like Earth, our closest neighbors in the cosmic family. The Sun produces neutrinos that pass through Earth undetected. Deep within the Sun's core, nuclear fusion produces not only light and heat, but also vast quantities of neutrinos. These nearly massless particles interact so weakly with matter that they pass through the entire Earth without stopping. Trillions of neutrinos from the Sun are passing through your body right now, even at night, when the Sun is below the horizon. Detecting these solar neutrinos requires enormous, highly sensitive detectors buried deep underground to shield them from other particles. The Sun whispers in a language that almost nothing can hear. Gravity holds the solar system together. Every object in the solar system, from the smallest grain of dust to the largest planet, is held in place by gravity. This invisible force connects everything, creating a delicate web of orbital relationships. The Sun's gravity dominates, keeping the planets in their courses. But each planet also exerts its own gravitational influence, tugging on its neighbors, capturing moons, and shaping the orbits of nearby asteroids. Without gravity, the solar system would fly apart. The planets would drift away into interstellar space. The moons would scatter. The rings would disperse. Gravity is the silent architect of celestial order. The Sun's gravitational influence extends far beyond Pluto. Even at the distance of the Oort cloud, nearly a light-year from the Sun, the Sun's gravity still holds sway. Objects in that distant realm orbit the Sun, however slowly. The true edge of the solar system is not defined by the planets, but by where the Sun's gravitational dominance ends and the influence of other stars begins. That boundary is vast. The Sun's gravitational reach extends perhaps 2 light-years in every direction. We live within a bubble of solar influence, far larger than most people imagine. The planets do not orbit in perfect circles. Johannes Kepler discovered in the 17th century that planetary orbits are ellipses, not circles. The Sun sits at one focus of each ellipse. Some orbits are nearly circular, like Earth's. Others are more elongated, like Mercury's or Pluto's. This means each planet has a point where it is closest to the Sun, called perihelion, and a point where it is farthest, called aphelion. The elliptical nature of orbits creates subtle variations in speed, distance, and received sunlight throughout each planet's year. The planets all orbit in the same direction. All 8 major planets orbit the Sun in the same direction, counterclockwise when viewed from above the Sun's north pole. This is called prograde motion. This shared direction is inherited from the rotation of the primordial disk that formed the solar system. The disk spun in one direction, and the planets that formed within it inherited that motion. Most moons also orbit their planets in the prograde direction, though some exceptions exist. The solar system moves as a coordinated ensemble, all spinning the same way around the central star. Retrograde motion confused ancient astronomers. Sometimes, when viewed from Earth, planets appear to move backward against the background stars. This is called retrograde motion. For centuries, this apparent reversal puzzled astronomers. Some proposed complex systems of circles within circles to explain it. The true explanation came with the heliocentric model. Retrograde motion is an illusion caused by Earth overtaking a slower outer planet, or being overtaken by a faster inner planet, as both orbit the Sun. It is a matter of perspective, not actual reversal. The Sun rises in the east and sets in the west because Earth rotates from west to east. Earth spins on its axis once every 24 hours. This rotation carries us from darkness into light and back again. Because Earth rotates from west to east, the Sun appears to rise in the east and set in the west. Stars, planets, and the Moon follow the same apparent path across the sky. This daily rhythm has shaped human culture since the beginning. Sunrise marks the start of day. Sunset marks its end. The turning of our world creates the cycle of light and darkness we call a day. A leap year is needed because Earth's orbit is not exactly 365 days. Earth takes approximately 365¼ days to complete one orbit around the Sun. If our calendar had only 365 days, the seasons would slowly drift out of alignment. To correct this, we add an extra day every 4 years, creating a leap year with 366 days. The leap year system is slightly more complex, with exceptions for century years, to keep the calendar accurate over long periods. Time itself requires careful calibration to match the rhythms of the solar system. The synodic period is the time between similar planetary alignments. The synodic period is the time it takes for a planet to return to the same position relative to Earth and the Sun. For Mars, this is about 780 days. Ancient astronomers tracked synodic periods to predict when planets would appear in specific parts of the sky. These periods differ from orbital periods because Earth is also moving. The apparent motion of a planet depends on the combined motions of both worlds. Planetary timekeeping is a dance of multiple orbits. Solar eclipses occur when the Moon passes between Earth and the Sun. During a solar eclipse, the Moon blocks the Sun's light, casting a shadow on Earth. Total solar eclipses reveal the Sun's corona, a ghostly halo of superheated plasma, usually invisible against the bright solar disk. Solar eclipses are relatively rare at any given location because the Moon's shadow traces a narrow path across Earth's surface. By coincidence, the Moon and Sun appear almost exactly the same size in our sky. This allows total eclipses to occur. In the distant future, as the Moon drifts farther away, this coincidence will end. We live in a special time for eclipses. Lunar eclipses occur when Earth passes between the Sun and Moon. During a lunar eclipse, Earth's shadow falls on the Moon, darkening it. Some sunlight filters through Earth's atmosphere and reaches the Moon, giving it a reddish color, sometimes called a blood moon. Lunar eclipses are visible from anywhere on the night side of Earth, making them more commonly observed than solar eclipses. The reddish tinge comes from the same phenomenon that colors sunsets. Earth's atmosphere scatters blue light and allows red light to pass through. A lunar eclipse is essentially the light of all Earth's sunrises and sunsets projected onto the Moon. The planets have magnetic fields of varying strength. Earth has a strong magnetic field generated by its molten iron core. This field creates the magnetosphere that protects us from solar radiation. Jupiter has the strongest magnetic field of any planet, thousands of times more powerful than Earth's. Saturn, Uranus, and Neptune also have significant magnetic fields. Mercury has a weak but detectable magnetic field. Venus and Mars have essentially no global magnetic fields. The presence or absence of a magnetic field depends on the internal dynamics of each planet, particularly whether it has a liquid, convecting core. The Lagrange points are gravitationally stable locations. In the gravitational system of two large bodies, like the Sun and Earth, there are 5 special points where a small object can remain relatively stable. These are called Lagrange points. The L1 point between Earth and the Sun is home to solar observation satellites. The L2 point, on the opposite side of Earth from the Sun, hosts space telescopes like James Webb. These gravitationally balanced locations are valuable real estate for spacecraft, allowing them to maintain positions with minimal fuel. The solar system has natural parking spots defined by mathematics and gravity. The Trojan asteroids share Jupiter's orbit. At Jupiter's L4 and L5 Lagrange points, roughly 60 degrees ahead of and behind the planet in its orbit, large populations of asteroids have accumulated. These are called Trojan asteroids, named after heroes of the Trojan War. They are gravitationally trapped in these stable regions, co-orbiting with Jupiter around the Sun. Smaller populations of Trojans have been found in the orbits of other planets, including Earth. Jupiter leads and trails armies of captive rocks on its journey around the Sun. Space probes use gravity assists to reach distant targets. Traveling directly to the outer planets would require enormous amounts of fuel. Instead, spacecraft use gravity assists, swinging past one planet to gain speed and change direction. The Voyager probes used gravity assists from Jupiter and Saturn to reach their distant targets. Cassini used multiple assists from Venus, Earth, and Jupiter to reach Saturn. Each flyby transfers a tiny amount of momentum from the planet to the spacecraft, accelerating it without burning fuel. Gravity becomes a tool, a cosmic slingshot, enabling exploration. The Juno spacecraft is currently orbiting Jupiter. Launched in 2011 and arriving at Jupiter in 2016, Juno is studying the giant planet's atmosphere, magnetic field, and interior structure. Juno's polar orbit takes it closer to Jupiter's cloud tops than any previous mission. Its instruments peer beneath the clouds, mapping the depth of storms and the structure of the interior. The mission has revealed that Jupiter's atmosphere is far more complex than previously understood, with storms extending deep into the planet. Juno continues to send back data, expanding our knowledge of the solar system's largest planet. The Perseverance rover is searching for signs of ancient life on Mars. Landed on Mars in 2021, Perseverance is exploring Jezero crater, the site of an ancient lake. The rover is collecting rock samples that will be returned to Earth by future missions. If any signs of past microbial life exist on Mars, they may be found in these samples. Perseverance is also testing technologies for future human exploration, including an experiment that produces oxygen from Martian carbon dioxide. The search for life beyond Earth continues on the dusty plains of Mars. The James Webb Space Telescope observes the solar system as well as distant galaxies. While famous for its images of distant galaxies, the James Webb Space Telescope also studies objects in our own solar system. Webb has observed Jupiter's auroras, the atmospheres of ice giants, and the composition of Kuiper Belt objects. Its infrared vision reveals details invisible to optical telescopes, including the chemical makeup of planetary atmospheres and the surfaces of distant moons. Even our nearest neighbors hold secrets that only the most advanced instruments can reveal. The Sun will eventually consume Mercury and Venus. When the Sun enters its red giant phase in about 5 billion years, it will expand to hundreds of times its current size. Mercury and Venus will almost certainly be engulfed by the expanding Sun. Earth's fate is less certain. It may be consumed or pushed outward to a more distant orbit. Either way, Earth will be scorched beyond habitability long before the Sun reaches its maximum size. The oceans will evaporate. The atmosphere will be stripped away. The inner solar system will be transformed beyond recognition. Life on Earth depends on the Sun's stability. The Sun is remarkably stable, varying in output by only about 0.1% over its 11-year cycle. This stability has allowed life on Earth to flourish for billions of years. Large fluctuations in solar output could cause catastrophic climate changes. We are fortunate to orbit a middle-aged star in the prime of its hydrogen-burning phase. The Sun is neither too young and variable, nor too old and unstable. Life exists in the comfort of a steady light. The solar system is one of billions in the Milky Way. Our Sun is just one star among an estimated 200 billion in the Milky Way galaxy. Many of those stars have planets. Astronomers have discovered thousands of exoplanets, worlds orbiting other stars. Some are rocky like Earth. Some are gas giants like Jupiter. Some orbit in the habitable zones of their stars. Our solar system is not unique. It is one example of a common phenomenon throughout the galaxy. The night sky is filled with other solar systems, each with its own stories waiting to be discovered. We've explored only a fraction of our own solar system. Despite decades of robotic exploration, vast regions of the solar system remain unexplored. No spacecraft has orbited Uranus or Neptune since Voyager 2's brief flybys. The Kuiper Belt contains thousands of objects we have never seen up close. The Oort cloud has never been visited at all. Even within the better-studied inner solar system, mysteries remain. Venus's surface is poorly mapped. Mercury's polar ice deposits are not fully understood. Mars's subsurface is largely unexplored. There is still so much to discover, even in our own celestial backyard. The study of the solar system is called planetary science. Planetary scientists study the formation, evolution, and current state of planets, moons, asteroids, and comets. The field draws on geology, chemistry, physics, and astronomy. It involves analysis of spacecraft data, laboratory experiments, computer simulations, and observations from Earth. Every world in the solar system has its own story. Planetary scientists work to read those stories, written in rock and ice and gas over billions of years. Understanding our celestial neighbors helps us understand our own world and the universe beyond. The solar system formed from a single cloud of gas and dust. Approximately 4.6 billion years ago, a vast molecular cloud drifted through the galaxy. Something disturbed it, perhaps a nearby supernova explosion, causing part of the cloud to collapse under its own gravity. As the cloud contracted, it began to spin faster, flattening into a disk. At the center, temperatures and pressures rose until nuclear fusion ignited. The Sun was born. The remaining disk of gas and dust contained all the raw materials for planets, moons, asteroids, and comets. Over millions of years, these materials clumped together, building the worlds we know today. Every atom in your body was once part of that ancient cloud. We are made of solar system stuff. The composition of asteroids tells us about the early solar system. Asteroids are essentially time capsules. Many of them have remained relatively unchanged since the solar system formed. By studying asteroids, scientists can learn about the conditions and materials present in the early solar nebula. Some asteroids contain primitive organic compounds, water, and minerals that date back to the very beginning. Missions like OSIRIS-REx and Hayabusa 2 have returned samples from asteroids to Earth for detailed analysis. These samples contain clues to the origin of the solar system and perhaps even the origin of life's building blocks. Comets may have delivered water to Earth. The origin of Earth's water is still debated, but one leading theory is that comets and asteroids brought water to the young planet through impacts. The inner solar system was too hot for water to condense during formation. But comets, rich in water ice, could have delivered their cargo over millions of years. The ratio of hydrogen isotopes in some comets matches that of Earth's oceans, supporting this theory. Other comets have different ratios, suggesting multiple sources. The water you drink may have once traveled through interplanetary space on the tail of a comet. The giant planets may have migrated in the early solar system. Computer models suggest that Jupiter, Saturn, Uranus, and Neptune did not always orbit where they are today. They may have formed closer together and then migrated outward. One popular model, called the NICE model, proposes that a gravitational interaction between the giant planets caused a period of instability about 4 billion years ago. This event may have scattered the asteroid belt, bombarded the inner planets with debris, and pushed Neptune into the Kuiper belt, disturbing the orbits of countless icy bodies. The current arrangement of the solar system is the result of a chaotic past. The late heavy bombardment may have scarred the inner planets. Approximately 4 billion years ago, the inner solar system appears to have experienced a surge of large impacts. This period is called the late heavy bombardment. Evidence comes from the ages of impact craters on the Moon. Many of the large basins that form the Moon's familiar face date to this era. If the NICE model is correct, the late heavy bombardment may have been triggered by the migration of the giant planets, which sent a rain of asteroids and comets into the inner solar system. The scars of this ancient storm still mark the faces of the Moon, Mercury, and Mars. The Sun's light takes different amounts of time to reach each planet. Light travels at nearly 300,000 kilometers per second, but the vast distances of the solar system still require time to cross. From the Sun to Mercury, light takes about 3 minutes. To Venus, about 6 minutes. To Earth, 8 minutes. To Mars, about 12 minutes. For the outer planets, the delay is even longer. Light takes 43 minutes to reach Jupiter, 79 minutes to reach Saturn, 2 hours and 40 minutes to reach Uranus, and over 4 hours to reach Neptune. When we look at Neptune, we see it as it was 4 hours ago. We are always looking into the past. The Sun's gravity bends light from distant stars. Einstein's general theory of relativity predicts that massive objects like the Sun curve the fabric of space-time. This curvature affects the path of light passing nearby. During a total solar eclipse, astronomers can observe stars that appear close to the Sun. Their positions are slightly shifted because the Sun's gravity bends their light. This effect, first confirmed during a 1919 eclipse, provided crucial evidence for general relativity. The Sun not only emits light, but also shapes how light travels through the space around it. The Voyager spacecraft will eventually go silent. Voyager 1 and Voyager 2, launched in 1977, have traveled farther from Earth than any other human-made objects. They are now in interstellar space, still transmitting faint signals. But their power sources, radioisotope thermoelectric generators, are slowly running out. Each year they produce a little less power. By the mid-2020s to early 2030s, there may not be enough power to operate any scientific instruments. Eventually, the Voyagers will fall silent. They will continue drifting through the galaxy, carrying their golden records, even after we can no longer hear them. The New Horizons spacecraft is exploring the Kuiper Belt. After its historic flyby of Pluto in 2015, New Horizons continued deeper into the Kuiper Belt. In 2019, it flew past a small object named Arrokoth, the most distant object ever visited by a spacecraft. Arrokoth is a contact binary, 2 lobes joined together, shaped like a flattened snowman. It is a pristine relic of the early solar system. New Horizons continues to operate, studying the Kuiper Belt environment and searching for new targets. The frontier of exploration keeps pushing outward. Interstellar visitors have passed through our solar system. In 2017, astronomers discovered the first known interstellar object to pass through our solar system. Named Oumuamua, it was a small, elongated body traveling on a trajectory that clearly originated from beyond the Sun's influence. In 2019, a second interstellar visitor, Comet Borisov, was observed. Unlike Oumuamua, Borisov showed a clear cometary tail. These objects are emissaries from other star systems, briefly passing through our neighborhood before continuing into the void. The solar system is not isolated. It is part of a larger galactic ecosystem. The solar system moves through space at over 800,000 kilometers per hour. The Sun, along with all its planets, is orbiting the center of the Milky Way galaxy. This motion carries us through space at tremendous speed. At the same time, the Milky Way itself is moving toward other galaxies. The local group of galaxies is falling toward the Virgo cluster. and the entire cosmic neighborhood is being pulled toward a massive gravitational anomaly called the Great Attractor. We are never still. The solar system is on an endless journey through the cosmos, traveling paths we cannot fully map. The Sun is a G-type main sequence star. Stars are classified by their temperature and color. The Sun is a G-type star, often called a yellow dwarf, though its light is actually white. G-type stars are middle-aged, middle-sized stars that burn hydrogen in their cores through nuclear fusion. They are stable and long-lived, providing conditions favorable for life. The Sun has been burning steadily for nearly 5 billion years, and will continue for another 5 billion before entering the next phase of its evolution. We orbit a very ordinary star, in the best possible way. Every planet in the solar system has been visited by spacecraft. From Mercury to Neptune, every major planet has been explored by robotic probes. Mariner 10 and Messenger visited Mercury. Venera, Pioneer, and Magellan explored Venus. Countless missions have studied Earth from orbit. Rovers and orbiters have mapped Mars. Pioneer, Voyager, Galileo, Juno, and Cassini have explored the giant planets. Some missions have landed on moons. Some have returned samples to Earth. Some have sent back images that changed our understanding of what worlds can be. We are no longer strangers to our own solar system. The search for life in the solar system continues. Mars, Europa, Enceladus, and Titan are all targets in the search for life beyond Earth. Mars may harbor traces of ancient microbial life in its rocks and soil. Europa and Enceladus have subsurface oceans that may contain the right conditions for biology. Titan has complex organic chemistry in its atmosphere and on its surface. Finding even a single microbe beyond Earth would transform our understanding of life's place in the universe. The answer may be waiting, frozen in ice, or buried in Martian soil. The solar system is our first step into the cosmos. Before we can explore the stars, we must master our own celestial backyard. Every mission to Mars, every probe to the outer planets, every sample returned from an asteroid brings us closer to becoming a spacefaring species. The challenges are immense. The distances are vast. The environments are hostile. But we have already sent machines to every planet. We have landed humans on the moon. We have touched the sun itself. The solar system is not the end of our journey. It is the beginning. And so, our gentle journey through the solar system draws to a close. We have drifted from the blazing heart of the sun to the frozen reaches beyond Neptune. We have visited volcanic moons and worlds where diamonds fall like rain. We have followed comets on their ancient paths and listened to the quiet whisper of spacecraft crossing into interstellar space. If your eyes are already heavy, that is just fine. Let the last traces of planetary light fade behind your thoughts, and let your breath carry you softly into rest. There is still so much more to discover. But for now, you have traveled far. You have learned enough. And the solar system can wait until morning. Thank you for joining me on this journey through the solar system. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the cosmos. There are more wonders waiting. More planets. More moons. More mysteries to drift through on quiet evenings. Rest well, and may the stars keep you company through the night. This has been Drowsy Discovery. Good night.